Okay, for the review of calculating pH and pOH, I've done several slides here, not to dump a bunch of information on you, but to give you a feel for what's happening with a logarithm. Logarithms are probably one of the more confusing things that students have to deal with, and they're even some confusing to me. But I think seeing the trends will help you be much more comfortable with them. Now this is a slide rule, picture of a slide rule, and I'm going to show that here in class. Folks at home won't be able to see it, but this is a slide rule. As I'm doing the log of 2 here, whoops, didn't mean to move that. Let's get that back. Okay, can I get that? Yeah, there we go. Okay, I'm going back up to here, and you see it's 3.1. 3.01. So the logarithm of 2, have I got the bottom scale here? Yeah, I got the bottom. So this guy is lining up with this, and I can actually take the logarithm of any number. So I can take the log of 3, and that's going to be 0.487 or something like that. So this guy, got to stop moving it. This guy is very, very helpful in terms of understanding one very important thing. It's probably the most important thing that I wanted to show with this. As I go from 1 to 2, what's happening to the distance between these lines? Smaller. They're getting smaller, progressively smaller. Now, if I look at some actual log tables, which I'm going to do a little bit later, you will see how that thing progresses. But I wanted you to get comfortable with this first. Watch what's going on as I go from 10 to the minus 1. Notice what I'm doing. I'm adding zeros. That is why the larger this negative number is, the smaller the real number is, because I keep adding zeros to the left of the 1. Isn't this fascinating data, or are the split ends more fascinating? Hi, Dana. So watch here, and you'll see what's happening with these powers. The other thing I wanted you to see is, look what's going on as the number out front gets bigger. 2, 3, 4, 5, 6. See, it's just substituting a different number in here on the far right, and we can look at that. This is what I'm talking about. This row of numbers is matching this. And now when we get to 9 and we get 1 10 to the minus 9 different, all of a sudden that baby rolls over to 10. And now we have a smaller number of zeros, which is why this 10 to the minus 8 is now our number and not 10 times 10 to the minus 9, because we have to stay in scientific notation. And the only way to do that is knock down the power of 10. Let's watch again. I've got a whole series of numbers here for you so you can kind of see what just happened. Okay, that 10 to the minus 8 now becomes the 1 times 10 to the minus 8. And now watch as I go down. You'll see now this row of numbers is 1 to the left of the original ending row. And that's as you would expect if it's 10 to the minus 8. And now the numbers go up, 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 up until I get to 10. And let's get somebody in the act here. Oh, edit, your name came up. How interesting. What do you think that next number is going to be? Okay. What is this number going to change into? Yeah, right. That's exactly what it does. And what is this number going to look like? Yeah, well, is the 9 going to stay here, or where's the 1 going to go when this goes to 10? Shh, give her a chance to look at it and see it for herself. Let's give you a little hint as you look up above at the end of the last series of numbers. What's going to happen to this guy on the next line? What? He's going to become a 0, and what will this digit become? Very good. Okay. And that is exactly what happened. So now our 10, see, here's the 10. So the 10 times 10 to the minus 8 is going to wind up being 1 times 10 to the minus 7, because we now have this last digit in one row over, or one column over, I'm sorry, column. And now we start again with 1 times 10 to the minus 7, and I didn't continue this down, but you can see what's going to happen and give you just a basic feel for that. Now let's look at the pattern for the number to the left of 10 to the x, which is what we were just doing, and we're going to compare that to the log of the numbers. So basically what I'm going to do is I'm going to take you from 1 times 10 to the minus 9 and take you on up to 10 times 1 to the minus 9. And what's that number actually going to be, Tony?
1 times 10 to the minus 8.
Yes, yes, this number is going to change to 1 times 10 to the minus 8. Now let's look at this with logarithms. You see the pattern now with the real numbers. Let's see the pattern now with the logarithms of the real numbers. Now what I did here is I substituted in more logarithms in the sequence than I gave you in that little chart earlier. Remember, I just gave you 3 numbers. I think it was 0.3 or 3, 5, and was it 9 or 8? Anybody have that little sheet? That little simple sheet? 0.3, 0.7, and 0.9, wasn't it? Yeah. So 0.3, a log of 0.3 is the number 2, the real number 2. And the log of 0.7, the log 0.7 is the real number 5. And 9, when we take the log, is 0.95. 8, when we take its log, is 0.9. But let's get a little pointer in here and let me show you our point as I talk to get you a better idea of what happened with these logs. Okay, 1 is 0. That's why when we have this number, this guy is the actual logarithm, right? Because we don't have anything to subtract from this guy. Okay, what's the log of 10 to the minus 9? Purge. What's the log of 10 to the minus 9? You're not going to find it down here. What's the log of 10? Minus log of 10 to the minus 9. Now, we're doing a pH now, and this is the hydrogen ion concentration. So what's the minus log of 10 to the minus 9? It is. Yes, it is 9. Good. Excellent. So, as this guy gets bigger, now we're going to subtract the 0.3, because if this number becomes a 2, we're going to have to subtract 0.3 from the 9 that we get from logging this real number. And the log is actually defined as 10 to some power, and that power becomes the logarithm. And you're going to see in just a minute how that relates for real. My wife helped me see something that I didn't realize before, but is actually true. And we'll see that at the end of this little part of the discussion. But this 0.3 now, what's the difference between 0 and 0.3? 0.3. Okay, the difference between 0.3 and 0.48? 0.18. Interesting. We went from a jump of 30 to a jump of only 0.18. A jump of 0.30 to a jump of only 0.18. Now, what's the difference between 0.48 and 6? 0.12 instead of 0.18. Notice how it's getting smaller? Just what we saw before, isn't it? On the slide rule? On the slide rule. Okay, between 0.6 and 0.70, we have 0.1. And between these guys, we got 0.08. You see the difference keeps getting smaller. So let's look now at the next sequence. And we'll take it down just like we did before. And now we're going from 0.7 to 10 times 0.7. And that becomes 1 times 10 to the 6, 10 to the minus 6. There we go. Now let's go ahead and look at the sequence again. And you're going to see exactly the same trend, aren't you? Okay, let's get rid of this guy. Okay, so the trend now is going from a 0.0 on down. Same old, same old. What are we going to end up with at the end of this sequence? Enrique, what's the new number going to be when I get to the end of this? We started at 10 to the minus 6. When we get to number out front of 10, what is the power of 10 going to be? Yeah, 10 to the minus 5. And you'll see that on the next page as we go through here. And I'm sorry?
Remember you said that the log of the 1 times 10 to the minus 8 is 8?
Yes, it is.
Then what happens when there's a
The
2?
minus log. Yes.
Oh, yeah, it's minus. What happens when there's a 2 times 10 to the minus 8? What's the log there?
That's what I was just telling you. The 2, if there's a 2 out here, this 2 here, gotta get another pointer. Here we go. So this 2 is sitting in front of this guy, right? That means when we take the log of this entire number, we do it in 2 pieces. First of all, we know the log of 10 to the minus 8 is 8. The minus log of 10 to the minus 8. Hydrogen ion or hydroxide ion concentration, which is what this is all about. But now we have to take the log of 2, which is the number out front, and that's a 0.3. So now instead of 8, it becomes 8 minus 0.3, which is 7.7. And that's the new log. As we get all the way up here, we're subtracting 0.95, and 8 subtract 0.95 becomes 7.05. See why it gets smaller?
Yeah.
Okay, and now when it gets to 1, that 10 to the minus 8 becomes 10 to the minus 7. Because now the number out front is 10, and the log of 10 is 1. You got to see a sequence. This took a horrific amount of time to create, but I think it's really good to see what's really happening in these numbers. Once you get that, it becomes less fearful. You know, it becomes manageable in your mind. Okay, now we have 10 to the 6 going 1 times 10 to the 6 going to 10 times 10 to the 6, at which point it now becomes 10 to the minus 5. And same old sequence. Okay, same deal here. So numbers go across, and we finally end up with, starting with 10 to the minus 6, we end up with 1 times 10 to the minus 5 again. Now let's apply it. This is so cool. 3 times 10 to the minus 6, 3 times 10 to the minus 6. Log of 3 is 0.48. Okay, so when I subtract, here we are, pH or pH will be 6, which is the minus log of 10 to the minus 6. Okay, 10 to the minus 6 here. And then we have the log of 3, which was 0.3. What was it? 0.48? 0.48. Okay, 0.48. And that's where we get this guy here. All right? So now when we subtract those out, it becomes 5.52. What I didn't show you before is that the exponent is really 10 to the minus 5.52. And what is the log of 10 to any power? It is that power, isn't it?
Yeah.
It's the exponent. And that's what the exponent is, and that's what the pH becomes.
But in this case, it has to be negative.
Yeah, well, no, this pH is positive because we did the minus log.
Oh, yeah.
Okay, the minus log of 6, or 10 to the minus 6 is 6. And the minus log of 3 is, instead of negative 0.48, it's a minus log. So when we logged it, we changed the sign. And because this is a positive number, it's now a negative number. Because we're doing the minus log. Minus log changes the sign of whatever the log is. Okay? So here we go. We took the log of 3. That gave us the 0.48. I'm just showing you the same thing in steps. And the 6 minus the 0.48 is giving us the 5.62, which is the log of the minus log. Minus log of the number. And the minus log, what? Well, if this were the hydrogen ion concentration up here, okay, when I take the minus log of both of these guys and I subtract the 2 out, what that gives me is the hydrogen ion concentration. Now, your minus 14 is if you wanted to change that to a POH. Okay? It's hard to keep those things straight until you've done that a few times. Yeah. Okay. So that wasn't a bad thing to come up with. It just isn't appropriate right here because you're mixing up a couple of things, which is what I expect you to do when you're just learning. Okay? Okay, here we go. How does this all apply to what we're doing in the homework tonight? You are going to have to understand that strong acids and strong bases, what do? They do? Yeah, let me rub it in your face. Yeah, look at that. Ionize 100%. Oh, I love this. This is so much fun. Okay. But wait, it's not going away. It's coming back in its weaker form. And now we're going to do our work here with that as a backdrop. Everything ionizes 100%, right? Oh, this is so cool. So, let's take a strong acid. And how do we know the strong acids? Oh, this is tricky. This is very, very tricky. What do we have here? No, not that guy. Where is he? Where'd he go? Oh, yeah, I put him here. Okay, and so, what are the strong acids? Ta-da! Cool, huh? Yeah. Okay. There's your strong acids. Hydrochloric, nitric, perchloric, and sulfuric. If you haven't got those in your head yet, you want to write those down because those guys are important. There's not very many of them, so those are nice to know. And in fact, for your homework tonight, I think they give you all strong acids and strong bases. I really should have taken this part out. R. There we go. X. There, you're gone. All right. Your history. But not really. I'm bringing you back. Oh, you little sweetheart. Here you go. V. Oh, there it is. Okay.
Yeah, Mr. Wiggles, who's Dana or Data?
Data?
Dana or Data? You said
Hi, Dana. You're like,
yeah. When you were talking to Eddie, you said Dana or Data. We were all like, we all looked
Oh,
at each other, like, what?
edit. I'm sorry. Sorry about that. Sorry, edit. So, at any rate, now we know what our strong acids are, right? So, those guys, you can count on them. And what is it that we can count on them for? Oh yeah, ionized 100%. Yay! Okay, now where'd I put you? Where'd you go? Holy moly, where'd I put you, little guy? Bottom left. Oh, thank you. I put him down here. Okay, so what is a strong base? Group 1 or Group 2? What's in Group 1 and Group 2? What's Group 1?
Alkali.
Alkali. What does alkali mean? Starts with a B.
Basic.
Basic. Yes. Okay. No, it's not boom boom. No. Okay. So Group 1 or Group 2 with hydroxide. Oh my. Oh, this guy should be an exponent. I'm going to fix that little dude. There we go. Okay. Yeah, I just have been creating this stuff recently here. So let's get this guy back down to a regular and parenthesize him. Whoops, parenthesized. Okay. So now we know what a strong base is. Yes? Have you copied that down? If you have copied that down, you have good information, and you will be able to identify strong and weak acids as well as strong and weak bases. Ooh, don't let you get lost over there. Here we go. All right. Yeah, we'll just leave you right there, little dude. I think I'm going to park you up here. Okay, so let's do one. Here we go. We've got a 2 molar hydrochloric acid, right? Let's just rewrite. 2 molar HCl. And actually the way we write that when we're doing problems is we will write it 2 molar HCl. 2 molar, and this, here we go, HCl like this. 2 molar HCl. Now, because we know, oh yes, we do know that, come on, here we go. We do know that it's going to ionize 100%, right? Oh, doesn't that just turn you on? Isn't that great stuff? Since it ionizes 100%, what is the concentration of hydrogen ions now? If this guy is a gas, he's together. And which guy am I talking? Okay, so if this guy is a gas, he is HCl. But as soon as he goes into water and becomes aqueous, he is no more. He is no more. And so what I'm going to say here is we got a hydrogen and we've got a chlorine. Okay? Whoops. Cl. L. There we go. So we got hydrogen and we have chlorine, right? That's hydrogen chloride, which is the gas. Now, as soon as I have this guy in water, they are together no more. And what I'm holding up in front of my class right now is a pen with a cap.
Oh my gosh!
Whoa! Hey, I tell you, this is a high-tech presentation. So, here is one pen with a cap on. This represents hydrogen chloride. Now, as soon as I put this in water, I no longer have, okay. How many pens with caps do I have now? 1. Okay, the cap is on the pen, and I have 1 pen with a cap. Now, I just took the cap off of the pen, and you at home can do this for yourselves. And now, how many pens with caps do I have? None. Oh, that was dirty pool. That was really dirty pool. He said the pen in my pocket. Okay, anyway. So, but in my hands, I have no pens with caps. Now, this represents the hydrogen chloride situation. and the hydrochloric acid, because as hydrogen chloride, he is this, and when I put them into water, they become separate entities. And there is no more of this guy. So, oops. Okay, as we look at what we have then, what is the molarity of hydrogen ion? When I drop this stuff, or when I bubble this stuff is what you actually do. When I bubble this into water, what's my hydrogen ion concentration? It's 2. The molarity is the concentration. Molarity, remember, is, let's do it on the acid side. Molarity is equal to moles over liters. If you've forgotten that, write it down. You need to know. You need to know. Write that down. Now, let's do another strong acid. Let's do the HClO3. HClO3, or O4. Let's do the O4. It's a little stronger acid. Okay, O4. Okay, so the HClO4. What am I going to have for a molarity of hydrogen ions if the molarity of the HClO4 is equal to 8? 8 molar. What is it? What's the molarity of hydrogen? Hydrogen ions. 8. Molarity is 8. Very good. So this guy is going to have the same molarity as this. Now, because this is a strong acid, how much of this is left in the water?
None.
None. All gone. Disappeared. Okay? To become the ClO4, the perchlorate ion, and the hydronium ion after it hits the water. But hydrogen ions for right now will suffice. All right, so let's take a look at a base. Let's do a real common one, sodium hydroxide. Now let's look back up here at the bases. Recall that group 1 or group 2 with hydroxide ions. Is that making you dizzy? Good. And we're here till 04. Okay, good. We got time. Excellent. Control Z. And there. Ah, come on. Can't get that guy to work. There we go.
Thank you, Mr.
You're welcome. Okay. So now we're dealing with sodium hydroxide, and sodium hydroxide is a strong base because he has a group 1 metal, sodium number 11. All right? And he is going to ionize how much? 100. Dun, 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 dun. Yeah, 100%. Okay, so we got this dude, and we got this dude. And there's no more of this dudes. These dudes are gone, and these guys are now what we have in the water as soon as they dissolve. Okay, so there's going to be none of this left. It ionizes 100%. All of that is critical in terms of what we're going to do in this little exercise that you have for your homework tonight. If you would all please turn to page 621 in your textbook, I'm going to do a problem for you. It is the first problem that is from that section. The other homework tonight is going to be doing the pH of finding the pH of an acid or the pOH of a base, and then changing the acid to the base concentrations, right? Yeah. You know how to do that. Or the pHs. I'm sorry, the pHs from one to the other. So, here we go. We're on page 621. And we're doing number 30. And here's how she works. Given? Fine. I'm modeling your homework. So, first of all, given, as I read this, what is the molarity? Aha! What is the big M, which is what over what? Moles over liters. Okay. What is big M for cesium hydroxide? And this is the way you write this. Cesium hydroxide goes down here as a subscript to the molarity. Anna, why aren't you writing? Okay, so the first thing they gave us was what we're supposed to find. If 3.0 liters, 30.0 liters, or milliliters, yeah, 30.0 mils of the solution, and what is the solution? That's the hydrobromic acid, HBr. 30 mils. Okay, this is a volume. This is called, I'm going to call this volume 1. Remember P1V1 equal P2V2? Yeah. Same deal. Okay, you got to keep the ones together. Okay, so in this case, the 1 is going to represent hydrobromic acid. And what's the molarity of hydrobromic acid? Oops, guess what I just did?
What?
I mixed that up. This is not HBr. This is the cesium hydroxide. How did I know that? Cesium hydroxide. So if this is V1, this is equal to M1, isn't it? Yes? Okay. So what's the molarity of cesium hydroxide if 30 milliliters of that solution is neutralized by 26.4 mils of the other guy, which was the HBr. And that's our second volume, isn't it? And you'll notice it says in the problem, by 26 mils, 0.250 big M HBr. So this is the molarity, and this is molarity 2. Molarity 1 is over there on the fine. So now molarity 2 is 0.250 big M. And that's HBr. It kind of helps to write the stuff in, then you know you've got those guys tied up right. If you put this molarity, I'm pointing to, if we put this molarity, oh, here we go, this volume with this molarity, we'd be in big trouble. Okay, our numbers would come out all wrong. Okay, so now it's plug and play. And the other thing that you have to realize with these guys is poly and monoprotic acids. And that's what the A is. H2SO4, mono or poly hydrogen ions? Poly. Okay. H2SO4, what's the value of A? 2. H3PO4, phosphoric acid. What's the value of A? 3. Okay. Sodium hydroxide, NaOH.
1.
Value, yeah, good. And let's do magnesium hydroxide. 2. Okay. See how that works? Aluminum hydroxide. Value of B is 3. Okay? That's how you deal with those guys. I don't think you have any of those polys in this assignment tonight. But when you get there, that's what you're going to do with the A's and the B's. Otherwise, the A's and the B's, you can act like they're not there. Or turn them to 1, either way. as long as they're monoprotic. Now we go ahead and we set up the problem. So we've got V1, 30.0 milliliters. That's V1, V2, V1 and M1. M1 is our unknown, CSOH, is equal to, we got mils again, 26.4 mils times a 0.250 molar. Now, do you see something that's a problem? Big M is moles per liter. But this is mils. How's it going to cancel? No can do. Well, hold on. Sit down. Just like with the gas laws. Just like with the gas laws. This guy, because he's mils, will cancel this guy when we do this to solve for M. 30.0 mils. And over here, 30.0 mils. And the mils cancel, right? That's it, folks. That's how you do this stuff. Say this.